Welcome to another video from explainingcomputers.com and to my annual quantum computing update. Specifically, in this video, I'm going to provide a brief overview of quantum computing, I'm going to report on some recent developments, and I'm going to highlight a potential future killer application. Or, in other words, I'm going to address the three key questions: what is quantum computing, who is creating it, and why do we need it in the first place? Conventional or classical computers are built from billions of transistors that are turned on or off to represent a value of either 1 or 0. In turn, this allows classical computers to store and process data using binary digits or bits. In contrast, quantum computers process information using quantum bits or qubits that can be represented by superconducting electronic circuits. Due to the strange laws of quantum mechanics, qubits could exist in more than one state or superposition at exactly the same point in time. This allows a qubit to assume a value of 1 or 0 or both of these numbers simultaneously. In turn, this enables a quantum computer to process a far higher number of data possibilities than a classical computer. In addition to assuming superpositions, qubits can become entangled. Entanglement is another quantum mechanical property and means that the state of one qubit can depend on the state of another. This is useful and powerful as it means that observing one qubit can reveal the state of its unobserved pair. Creating, sustaining, manipulating, and error-correcting qubits is very hard indeed. But significant progress does continue to be made. So, let's now turn to the work of today's quantum computing pioneers. One of quantum computing's trailblazers is IBM with its initiative called IBM Q. Since 2016, IBM has provided access to cloud-based quantum hardware, and in January 2019 unveiled the IBM Q System 1, which it describes as the first integrated quantum computing system for commercial use. Also advancing quantum computing are Intel, who in January 2018 announced a quantum processor called Tangle Lake. According to the company's website, Intel is targeting production-level quantum computing within 10 years, and expects the technology to start to enter its commercial phase around 2025. Google is also developing quantum hardware and software, and in June 2019, Harmut Neven, the director of its Quantum Artificial Intelligence Lab, reported that the power of Google's quantum processors is now increasing at a doubly exponential rate. This has already been termed Neven's law, and suggests that we may reach the point of quantum supremacy, where a quantum computer can outperform any classical computer by the end of 2019. Also in the game, in February 2019, Microsoft announced the Microsoft Quantum Network to advance quantum computing, and which formalized a previous coalition of partnerships. In May 2019, Microsoft also reported that it will open source its quantum development kit, which includes its Q-Sharp quantum computing programming language and compiler, as well as quantum computing simulators. Another long-term quantum computing pioneer is D-Wave Systems, which in October 2018 launched a cloud-based quantum application environment called Leap. This provides real-time access to a D-Wave 2000Q quantum computer, and in March 2019 was expanded to provide access in Japan and across Europe. Other quantum computing pioneers include Alibaba in China, who in March 2018 launched its superconducting quantum computing cloud. Also offering a quantum cloud platform are Rigetti, with other pioneering quantum computing pureplays including Quantum Circuits and IonQ. Hopefully, what this brief summary has demonstrated is how quantum hardware, software, and service provision are now advancing at pace. It's therefore wise for us to question just what quantum computers are going to be used for. quantum computing's first killer application is likely to be quantum molecular modelling, also known as quantum chemistry. And this probably sounds rather abstract, rather removed from traditional everyday computing. But if you give me a few minutes, I'll explain why quantum molecular modelling will help to move computing into a new age. Now, molecules are multiple atoms bonded together. So, for example, a water molecule contains 2 hydrogen atoms and 1 oxygen atom. Or a caffeine molecule contains 8 carbon atoms together with 10 hydrogen, 4 nitrogen and 2 oxygen atoms. So why am I telling you this? Well, even though a caffeine molecule, for example, looks fairly simple, a conventional computer cannot model one at the quantum level. Now clearly we do have software that allows us to build models of molecules, such as the MolView package we're looking at right now. And some existing packages can also simulate the basic chemistry of how molecules behave and interact. But none can accurately model the subatomic particles inside each atom due to the extraordinary number of data possibilities that would be involved. And this means that we've yet to build an accurate simulation of any molecular system using a conventional computer, and we probably never will. Because molecules are quantum in nature, the hardware required to simulate them also needs to be quantum. And this is why quantum computers will become so important. We also already know that quantum molecular simulation can work. For example, in 2017, some IBM engineers reported in Nature that they successfully used a quantum computer to model a beryllium hydride molecule. And then in July 2018, this paper was published in the journal Physical Review X, again reporting on success using quantum computers to run molecular simulations that could not be run on a classical computer. There's also now a startup company in Germany called HQS Quantum Simulations, which is developing software for the quantum simulation of molecules and processes in order to disrupt the way in which specialty chemicals, materials, agrochemicals and drugs are developed. Today, we cannot accurately simulate what is going on in a cup of coffee. And yet, 10 or 20 years from now, we could be using quantum computers to run very complex molecular simulations. And this would transform our understanding of chemistry, physics, biology, and in turn it would change our practice of engineering and medicine. Imagine in the future if you got ill, a future doctor or AI could build a quantum simulation of your whole anatomy, your whole body, and then also build quantum simulations of different drugs and test those drugs in the quantum simulation of your body, and they could maybe test thousands of drugs over a simulated period of time of many weeks, and they could do all of that in a few microseconds. That would be truly revolutionary. And it won't just be medicine. We'll be able to use quantum molecular simulations to simulate things like the climate, predict the weather, things like that, develop new materials, test out new ways of building things, all those kinds of things. So it is the potential to use quantum computers to build accurate simulations of the physical world that will make them so revolutionary. To put what I've just been talking about in context, let's turn to a model that I call the 5 Ages of Computing. This was introduced in my book Digital Genesis and signals how the initial historical phases of early computing and personal computing had a focus on using computers to perform computation. But then, around 20 years ago, we entered the network computing age, in which computing has additionally been focused on communication. However, today we are entering the cognitive computing age, with the focus expanding once more to include the use of computers for prediction in addition to communication and computation. Cognitive computing is primarily associated with the rise of artificial intelligence, and certainly it will be technologies like neural networks that will allow computers to learn from sampled data and to predict appropriate responses when presented with data they've not encountered before. However, as I've just discussed, quantum molecular modelling will also prove an important aspect of the cognitive computing age. This is because quantum simulations are likely to be used to vastly increase our understanding or our cognition of the physical world, and in turn to improve our lives based on quantum predictions of how complex molecular systems will behave. Looking further ahead, the final computing age of cyborg fusion involves the physical synthesis of human beings and machines. This I've discussed in a video on my Explaining the Future channel, and is likely to rely on quantum molecular simulation to assist in the redesign and proactive evolution of ourselves. Quantum molecular modelling is very different to most of today's computing applications. This said, across history, the most revolutionary new technologies have always been used to achieve new things rather than to do old things in new ways. And it's therefore very reasonable to predict that most of tomorrow's quantum computers will spend most of their time executing quantum algorithms that most people today cannot even imagine. If you want to know more about the future of computing, you can look in my book, Digital Genesis. But now that's it for another video. If you've enjoyed what you've seen here, please press that like button. If you haven't subscribed, please subscribe, and I hope to talk to you again very soon.